Okay. So further writing down the basic properties of alpha, beta, and gamma, we have another property related to alpha, beta, and gamma because we uh, discussed in the basic nature of alpha, beta, and gamma that alpha is a positively charged particle, beta is a negatively charged particle, and there is no charge on gamma. So charges are included in alpha, beta, and gamma. So that's why we can also consider electric field and magnetic field because we have charges for alpha and beta. So definitely if we place these two particles in electric field or in magnetic field, so definitely because of the same charge or like unlike charge, there is force of attraction or force of repulsion between them. So let's suppose if we have electric field, so let's suppose we have two plates parallel to each other, and one side if we consider positively charged plate and the other side is negatively charged plate, and if we consider a source, let's suppose this is a source of radioactive material, and from this source all the three type of radiations are coming out, alpha, beta, and gamma. So if we start with alpha, so let's suppose alpha emits out from the nucleus of this element. So what do you think, in which direction alpha deflects, or what will be the pattern of the movement of alpha particle when it passes through this electric field, because electric field travels from positive to negative. So electric field is constantly traveling from positive to negative between these two plates. So when alpha starts to pass through this two plate setup, so what will be the deflection?
Alpha will go towards negative side.
Right. So alpha deflects towards negative side because alpha itself positive. So positive negative attracts. Right. So this is the pattern of the alpha particle. It deflects towards negative. Second, if we talk about beta, so definitely beta is opposite to alpha. So it deflects towards positive. This is the deflection of beta. And finally, no charge on gamma. So gamma travels
Yeah,
straight
so it's
without any,
straight.
yes, without any change in direction. It travels straight. Now there is one more important thing to observe in this pattern. If you observe the angle of alpha, like if you compare from the center, so this is the angle of deflection for alpha. This is the angle of deflection for beta. So these two angles are different from each other, and it is always different from each other. There is a specific reason for this. That's why we always draw the field pattern and the deflection of alpha and beta in opposite angles or like in different angles. The reason is very simple. If we first talk about alpha, so alpha is a heavy particle and the charge of alpha is also greater than beta. So alpha is heavy. So to deflect alpha particle, right, because it is heavy, so it takes more time as compared to beta. Beta is a light particle. So if any object is very light, so it is very easy to move that object. In the same way, beta is a light particle as compared to alpha. So it is very simple to bend or deflect beta particle as compared to alpha because alpha is heavy as compared to beta. So definitely to deflect alpha, we required more time or we can say more force to deflect alpha. That's why the angle of deflection for alpha particle is small as compared to the angle of deflection for beta particle, right? So alpha deflects with a smaller angle because of heavy mass. Or we can say because of greater mass than beta. And for beta, we can say beta deflects with greater angle as compared to alpha due to small mass, right? So this is the difference between the pattern of alpha and beta because both have different masses, and that's why the deflection shows this difference also between these two particles, right? And secondly, if we place the same source in magnetic field, because electric field, like we discuss about the chapter of electromagnetism, and we observe that electric field, magnetic field are already linked together. So in the same way, if we place this radioactive element in the magnetic field, so definitely because of magnetic field, it also impacts uh, the path of alpha particle and beta particle. So let's suppose if we consider the same source in magnetic field, magnetic field. So for magnetic field, definitely we need to consider the magnetic field. So magnetic field is from north to south. So for example, if we consider magnetic field into the paper, right? Into the paper, if we make cross, so let's suppose this is the pattern of the magnetic field which is into the paper. So this is the pattern of magnetic field which is into the paper right now. Cross means into the paper. Now, according to Fleming's left hand rule and Fleming's right hand rule, we already know about these two rules. We apply Fleming's left hand rule when we need to find out the direction of the force, right? So, if you need to find out the direction of the force on any particle or any conductor, we used to apply Fleming's left hand rule. And if we need to find out the direction of electric current or induced current, so then we apply right hand rule. So in this situation, we already know about the direction of current, because if we are taking alpha particles, so alpha is itself positive, and conventional current always flows from positive to negative. Okay. So let's suppose if we have radioactive element, and first of all, starting from alpha. So according to alpha, alpha is positive and alpha deflects in this direction, and y in this direction. If you consider left hand rule, so according to left hand rule, the first finger points into the paper, right? So first finger is pointing towards the screen, right? And the direction of current is in upward direction. Okay, so the direction of current is in upward direction. And for because we are talking about alpha, so alpha is positive. So when positive is moving, when alpha particle is moving, it means positive charge we have. So it is the same pattern of electric current, because electric current travels from positive to negative. So in the same way, if you consider alpha particle, so it travels from positive to negative. So that's why if you apply Fleming's left hand rule, so the direction of current is in upward direction. Okay. And secondly, if we talk about the magnetic field, so magnetic field is into the paper. And if we talk about the direction of force, right? So your thumb direction will be towards left hand side. Okay. So it will deflect towards left hand side. I will also share picture for your reference. So if you apply Fleming's left hand rule, so it will be very easy to identify. Otherwise, if you got the same direction, like same pattern of the magnetic field in your exam question, so you can just directly identify the answer. But otherwise, the question is how we know that this is the direction. So you can identify the direction with the help of Fleming's left hand rule. And in the same way, we already know about the direction of alpha. So beta is in opposite charge. So when beta is like in opposite charge, so you can identify the direction of beta very easily. Beta is always like in opposite direction to alpha. So if alpha is deflecting towards left hand side, so definitely beta deflects towards right hand side. So then we have for beta. And again, we also need to consider the same deflection angle, because beta is light, so it deflects with greater angle. And this is for gamma, right? Any question, any confusion in this?
No, but can you just go up 1 minute, please? Can you like scroll up? Okay, thank you.
Okay. So basically we apply Fleming's left hand rule. Okay, so these are two other properties related to alpha, beta, and gamma, and it depends upon the same idea of Fleming's left hand rule, especially for magnetic field, because electric field is very easy to identify. So that's why the magnetic field is a typical one as compared to electric field. Now, in this chapter, we started the concept of radioactivity. So if we consider the concept of radioactivity, so radioactivity means emission of particles or emission of energy from unstable nucleus, right? So we also discussed about equation, alpha, beta, and gamma, how to write proper equation in the case of alpha, beta, or gamma. So this is the scenario. Now the second thing is, if we want to calculate that number, like how much the mass of the nucleus decrease, how much the energy of the nucleus decrease. So this is the question. Okay, so how we find out that number? So that number can be identified with the help of half life, the concept of half life, right? Okay. So let's suppose if we want to find out that missing number from the nucleus, let's suppose if the total number of the nucleus is 100, and let's suppose it starts to emit out that number of particles one by one, like 1, then 2, 3, 4. So number starts to decrease 99, 98, 97, 96. So definitely there must be like some specific time. Like if we observe that element for 1 month, so we calculate that in 1 month how much mass decay from that nucleus, or like in 24 hours, in 1 year, in 5 months. So there is like different time slot for each type of radioactive element. Some elements take more time, so they have more half-life, and some elements decay quickly, so they have short half-life. So the topic of half-life is very important in this chapter, and it is very easy also, because we just need to find out the half of the element, half-life. Definition of half-life is very simple. It is like a time taken for the radioactive sample to reduce its radioactive nuclei to half of its initial value. So just like we discussed about 100 value, so if something is starting from 100, so we find out or we note down the time in which that 100 decreases to 50. In the same way, if something started from 1000, so we have to record the time, like how long it will take to reach the value of 500. So this is the concept of half-life. And there is another term in this half-life which is called activity. Like for this whole process of decaying of the nucleus into the half value, so that is called activity. So in short, we can use this term of activity. So activity can be defined as the number of emission per unit time. So it will be like 100 emissions per second, 100 emission uh, per week. So it depends upon value to value. Okay, so it is not compulsory that it will be same for every element, because in the start of radioactivity we mentioned that it is a random process, so it depends upon material and the nature of material. It is not compulsory that it is always same for every element. Okay, and the method of counting this half life is very simple. Let's suppose if something is starting from 200, we know that if we divide it by 2, so then it converts into the half of its original value. Then if we further divide it by 2, it converts into the half of original value, and so on. But the important thing is we need to find out the time of first half life, time of second half life. So this is important. Okay, so for half life we can write symbol like this: t half, half life. Okay, now the concept is, uh, what type of question we have related to the half life, how to identify that concept of half life. And there are different detectors available now in laboratories. In front of that detector, you can place radioactive element, and that will give you the reading. So for a certain interval of time, you can record that reading, like how much value decreases in a certain interval of time. So from that interval of time, let's suppose if you observe that radioactive material for 20 minutes and you observe a specific value, so now after that you can automatically multiply that number to find out, like in 1 year it will decay to this specific value. Okay. So for example, for the half life, we have many MCQs that will help you to practice the concept of half life. Half life is just to convert into the half of the original value. Very simple. Okay. So this is the first question. We have question number 2. So in question number 2, a reading is taken every 10 minutes. So you can see this is another experiment type in which they are taking reading after every 10 minutes of number of emissions per second from a radioactive source. What is the half-life of the source, right? So we started from 0, and at the 0 value is 800, and after 10 minutes interval we have new reading, then another 10 minutes interval new reading, then another 10 minutes interval a new reading, and so on. Okay,
Can
so
we say 20 minutes? Because it's like
Yes,
half of
sure.
the original emission.
yes, so basically you have to find out the half, and half of what? Number of emissions per second. So this is the initial value. So if you divide this 800 by 2, 800 into half, that gives you 400. So that is equals to 20, right? Option B. So it is very simple. We don't need to apply any specific equation formula. So it is very simple. So this is basic question from half-life. And you can also draw a graph of half-life, because something is decreasing. It means exponential decay, or just like an inversely proportional graph. It gives you this type of pattern. So for example, in question 3, the graph shows how the decay rate of a radioactive source changes with time. What will be the activity at 8 days? So basically some numbers are missing. This is 4, 6, 8 and 10. So now you can see we started from 4,000. So always focus for the initial value. This is the initial value. So initial value is 4,000. So the half of 4,000 is 2,000. So this is 2,000 and this is the first half life. This is the first half life and 2,000 takes total 2 days to decay. Like after 2 days, it decays into the half of its original value. It means after every 2 days, the value of the nucleus or the value of that decay decreases to half of its original value, right? Now further you can see at 1000, we have second half life. So this is second half life at 4. Okay. In the same way, their question is for 8 days. So we started from 4,000. 4,000 divided by 2, which is equals to 2,000. This is first half life. Then it further decreases to 1,000. Then it further decreases to 500. And it further decreases to 250. So it means that this is the first half life. It takes 2 days. And this is the second half life. 2 plus 2, total 4 days. Then third half life. 4 plus 2, 6 days. Then fourth half life. 6 plus 2, 8 days. So after 8 days, you will reach the value of 250, right? So it means the final answer is option C. Any question in this?
No, it's clear.
So it is very simple.
Yes.
Just perform simple calculation. It starts from the original value, make it half, then take the new value, then again decrease to half, and continue the same process. So this is the easiest way and this is the simplest way to find out the half life. Otherwise, if you want to try any shortcut, so maybe there is a chance of getting a wrong answer. So never try for a shortcut. Just simply follow the simple process of decreasing the value into the half of its original value. Okay. Question number 4. A sample of a radioactive isotope has an initial rate of emission of 128 counts per minute and a half-life of 4 days. So how long will it take for the rate of emission to fall to 32 counts per minute? Okay. So now this is the initial value. And it consists of a half-life of 4 days. This is the half-life. Now, how long will it take for the rate of emission to fall to 32 counts per minute? This is your targeted value. So we have to reach this target value. So process is again very simple. Start from the same. We have 128, decrease into half, it becomes 64. 64 divided by 2, 32. So now you can see we got the value 32. And according to the calculation, it is mentioned half-life is equals to 4 days. So for the first half-life, it total takes 4 days. For the second half-life, it takes more 4 days. So 4 plus 4, 8. So it means after 8 days, this element reached the value of 32 counts per minute, right? So this is the easiest pattern to find out the half-life. In the same way, question number 9, a powder contains 400 mg of a radioactive isotope that emits alpha particles, and the half-life of the isotope is 5 days. So what mass of this isotope remains after 10 days? Starting from 400 mg of a radioactive isotope that emits alpha particle, and the half-life of the isotope is 5 days. What mass of the isotope remains after 10 days? Half-life is 5 days, right? After 10 days means it will like the second half-life of the element, because first half-life takes place after 5 days. So 400 decreases into the half, that is 200. Then 200 decreases to the half, which is 100. This is the first half-life. It takes 5 days. And this is the second half-life. So 5 plus 5, 10 days. So after 10 days, mass will remain 100 mg. Okay. And with the concept of this half-life, we have another idea which is called background radiation. For example, if we are like performing an experiment and you are using a device to record the value of radioactive sample, now the question is, in our surrounding we have some natural radiations, like we are getting radiations of sun, right? So that radiation of sun can also be included with that the source of radioactive material. So some background radiations are also included naturally in our surrounding, but those radiations are not harmful. But still, that radiations can be detected by radioactive detector. So when we are performing experiment, so in your experiment values, background radiation values are already included. Okay. So if we talk about the background radiation concept, background radiation. So background radiation is, in simple words, we can say radiations naturally present in our atmosphere. And these are not harmful. Examples of background radiations are cosmic ray, number two, nuclear reserves, buildings or rocks, nuclear waste. So, these are the sources of background radiation, and these radiations are naturally present in our surrounding. So, before starting experiment, just turn on that device and let it open for like 2 or 3 minutes. So, after 2 or 3 minutes, the counter shows you some specific reading, just like this. In this question, you can see in a laboratory, a detector of ionizing radiation records an average background count rate of 8 counts per second. So when we turn on the counter, so it shows you some reading 1, 2, 3, 4, any value according to your surrounding. So that is the background radiation. Okay. So we record this value that 8 counts per second is the background radiation. Then we start experiment with radioactive material that we are using in our experiment. So in this question, it is written clearly that we have average background radiations, which is 8 counts per second. A radioactive source is now placed close to the detector. So now count rate rises to 200 per second. Now the question is, what is the count rate due to radiation from radioactive source? So this is background, right? So we need to subtract this value from this one. Because 8 is the background radiation, 200 is the total value. So actually 192 counts per rate is for radioactive source. Okay. So this is the concept of background radiation, and it is very important to consider, otherwise it will change the value, or it will change the results for the half-life of the element or the calculation for any specific radioactive element, right? Any confusion in this?
No.
Okay. Question number 13, you can see we have very frequently asked question related to the half-life from the topical past paper file. It means you will find more questions related to half-life in your past papers as compared to any other topic of nuclear physics. So a radioactive source produces a count rate on a detector of 1600 counts per second. After 32 hours, count rate has fallen to 100 counts per second. Both count rates have been corrected for background radiation. So what is the half-life of the source? So now we have to find out the half-life. So initially we started from 1600, that is the value of detector, and after 32 hours it decreases to 100. And there is no background radiation, it is corrected for background radiation. So in again we have to follow the same procedure. We start from 1600. 1600 divided by 2, it gives you first half life. Then it further decreases into half, gives you 400. It further decreases into half, 200, and one more half-life, which gives you 100, which is our targeted value. Okay, so this is our main target. We have to reach this value after half-life. So first half-life, this is second half-life, and then we have third half-life, and this is fourth half-life. So we have total 4 half-life in this process. Now the total time is 32 hours. So if we divide this 32, 32 hours is the total time, and we have 4 half-lives. So if we equally divide this 32 into 4, so the answer is equals to 8. 8 hours. So basically every half-life takes 8 hours, like this. So after every 8 hour, element starts to decay into the half of its original value. So this is another pattern of the question related to the half-life, right?